So this morning, I'm going to start talking about KKT conditions for NLO, and I'll explain what all that means. So let's get right into it. What we're interested in here, and this is going to be a little bit technical, is to look for optimality conditions for a local minimizer, or even weaker, just for a stationary point of a nonlinear optimization problem. So I'm taking a step back. I'm going to a problem that no longer has integer variables. There's one objective function f of x, and there are m constraints gi of x, and I assume that they're all twice continuously differentiable. For the moment, I don't need convexity, but note that you often have additional structure, and I'll give some conditions later on that show what it looks like if you have this additional structure. So this is the problem that we're interested in, and we would like to know if somebody gives us a point and tells us this is a stationary point, or this is an optimal solution, can we check it quickly? So how do we check somebody's homework when they solve this problem? That's the goal of this lecture. And so a couple of definitions, and we've seen these before. The feasible set of a nonlinear optimization problem is just the set of all points x in Rn such that all of the constraints are satisfied. So G is now the vector of these individual constraints. It's a vector of length m, and component-wise they're all less than or equal to 0. And we had looked at the definition of local and global minimizers, but we don't really need it for this lecture. So I just put it in there because otherwise the slide would have been a little bit empty. But just as a reminder, a global minimizer is the lowest, is a feasible point that's in the feasible set such that there exists no point that is lower than this x star feasible point inside the feasible set. And the local minimizer is defined almost in the same way, except we look at only at a neighborhood of the current point, and we say that it is a local minimizer if there's no better point inside a neighborhood intersected. This should be an intersection. This is a bad mistake. This should be the other way around, an intersection with that neighborhood. What we're really interested in is conditions that are easy to check for optimality. And you may have seen this condition for unconstrained first order condition. So a local minimizer, if you have a local minimizer, then it follows that the gradient at that point is equal to 0. And in one dimension, that is easy to visualize. If you have a function and you have a local minimizer, then at these two local minimizers, if I take the gradient, then the function is flat there. So the tangent line at the function is flat. So here grad f is equal to 0, and here also grad f is equal to 0. Now, before you get too excited that we've now solved the problem, just one caveat. There's another point, namely up here, where grad f is also equal to 0, and that's a maximum. So this is only a necessary condition, meaning if you have a local minimizer, then it follows that the gradient is equal to 0, but it's not the other way around. It's not a sufficient condition. Sufficient conditions are stronger, or they're different. And so what we're interested in is to find a condition that allows us to rewrite this in the constraint setting. And this line here sort of gives an insight into what we're going to do in this lecture. So if I say that the gradient is equal to 0 at f star, then that's equivalent to saying if I take any vector s in Rn and I form the scalar product with f star, then the scalar product is 0. Right? And that's just because the vector itself is 0, so S transpose 0 is 0. That's a very simple conclusion there. S transpose f star is S transpose 0, which is 0. Another way of thinking about this is that the set of directions in which I can have a descent direction, so a descent direction is a direction in which I can reduce the objective function, that set of directions is empty. So this is a more involved, or looks a bit more involved, but this is the condition that we're going to generalize to the constraint case. And so what this says is there are no strict descent directions at x star. So if you look at this, if you're here, you can't, locally you cannot go downhill, and similarly here you can't go down here. But if you're at a different point, say this point here, then there exists a direction, this one here, so the direction in this direction here, where grad f transpose s is less than 0. You have a descent direction. Locally, you're reducing the objective function. And so what we need to do to generalize this is we must say what is a feasible direction, because in the constraint case, we can only do this for feasible directions. And then we would like to have a condition that allows us to check this very complicated looking condition, the fact that there is no feasible descent direction. That's a very difficult condition to check. We want something similar to a gradient condition that we have up here, something like this. So that's what we're going to do in this lecture. Very simple. And it's only going to take another 15 slides. Okay, so first of all, here are feasible directions. So that's kind of obvious if you draw a picture. There's a feasible set here, bounded by this blue line. And feasible directions are directions that go into the feasible set. So if you're at this point here, then you move in this direction, then all the points in this direction are feasible. Infeasible directions are the ones that go outside the feasible set. So that seems easy to do. So let's see if we can do this mathematically. And so our friend here is the Taylor series approximation. So everything we derive in optimization is based on Taylor series expansions. There's very little else that goes on in continuous optimization. So what we're going to do is we're going to look at some point x star, and we'll take a small step from x star, and we're going to see what happens to the function value for one of the constraints, so gi of x star. And I'm going to do this first for equality constraint problems. So I changed our problem to only have equations because it's slightly easier, and then I'll tell you how to generalize it to inequalities. So for equations, I can just do a Taylor expansion with around x star, and the first order Taylor expansion gives, first order Taylor expansion gives me the constant term, which is gi of x star, and then the gradient at x star, scalar product with the step, plus higher order terms, this little o of delta. Do you know what that means? If not, I think you do, good. It essentially means that this term goes to 0 even if you divide it by delta star. So another way of thinking about it, if you're twice continuously differentiable, then you can replace this by a big O of delta, norm of delta squared. Okay, so if we are at a feasible point, then gi of x star is 0, and this direction looks like delta transpose gi star. And so there's a reminder what this means. So a sufficient condition for feasibility then is that a direction S, scalar product with gi, is equal to 0. So in other words, I will stay close to being feasible if this term is 0. So that's going to be our feasible set of feasible directions. The set of feasible directions are all the directions whose scalar product with the constraints is equal to 0. And the reason we're doing equality constraints is because this makes, I don't need to worry about which side of the inequality I'm on at this point. Okay, so here's an illustration again for the same feasible set. So the feasible directions turn out to be the tangent directions to the feasible set. The feasible set now, the nonlinear feasible set, is just a single line. There's just one constraint. And there are 2 points, the green and the purple point. And if you construct the outward normal, that's the gradient of your function. And then the directions that are perpendicular to this outward normal are the feasible directions. So S transpose G star equals to 0 means these two directions are perpendicular to one another. So those are feasible directions at 2 points. they're only feasible when you take an infinitesimal step, right? I mean, if I go too far along this direction, I'm infeasible, but I'm only interested in what happens if I take an infinitesimal step at this point. So how do we derive these feasible directions? So here's just a simple example. I actually now have a nonlinear feasible set with inequality constraints. I have two inequality constraints. The red constraint says that I have to lie inside the circle, and the blue constraint says that x2, which is on the y-axis here, has to be above x1 squared, which is this parabola. So the feasible set is this purple area there, the intersection of those two sets. And at 0, 1, for example, I get the directions that are plus and minus 1. That's just evident because at that point, I only need to look at this constraint. And at 1, plus minus 1, 0, so those are these 2 points here, I get, 0, 2, at this point, I get these two directions. Okay, so they're not hard to derive. Okay. Now, when we want to derive stationarity conditions, we need a regularity assumption, and these are called constraint qualifications. The easiest way to think of a constraint qualification is that they imply that locally the problem looks like a linear problem. So the constraint locally in a small neighborhood of your point look just like linear constraints. And if you think about that for a moment, what we've been doing is we're taking gradients of the constraints, so we're linearizing the constraints, and so it makes sense to think that that would be a useful assumption, that this linearization locally tells us all we need to know about the constraints. And so a consequence of that is that if you have a problem that has linear constraints, then you don't need a constraint qualification. It's automatically satisfied because your constraints are linear. For nonlinear constraints, you need something like, for example, a linear independence constraint qualification. So this just says that the constraint normals, if I take all my constraints, then they are linearly independent. And there's alternative assumptions that I can make, but basically a constraint qualification says that I'm locally, my constraints are described by my first order Taylor expansion. Okay, so now I'm in a position to write down necessary condition or first order optimality conditions. So we're going to say that X star is a local minimizer up there in the third line. Then it follows that I cannot find a strict descent direction. So remember, strict descent directions are the ones that reduce my objective function. So the scalar product between the direction and the gradient is strictly negative. But I also have to make sure that I stay feasible, and so the condition for a feasible direction that we just derived is that S transpose GI star is equal to 0. So this is now fewer directions than I had previously. So previously, if I'm in the unconstrained case, let me see if I can draw this here somewhere. So in the unconstrained case, I need to look at all possible directions. And it's probably enough to look at the basis of R2, for example. In the constraint case, if in addition I also have some nonlinear equality constraint that goes through here, then at a local minimizer, I'm only going to look at directions that infinitesimal at least stay feasible. So this is actually a smaller set of directions. There's just these two directions here, for example, that I need to take into account. And in particular, you can, by inspection, you can see quickly that if you went into this direction here, there's this other direction, this green direction, you would reduce the objective function if you went into this direction, but that's not a permissible direction for the constraints. You would violate the constraints immediately. Okay, so this is the key lemma then that says that this unwieldy condition here, that there are no strict feasible descent directions, so the set of all directions that give me strict descent and are feasible is empty, is equivalent to this much simpler condition, the existence of Lagrange multipliers, such that I can write the gradient of my objective function, I can express the gradient of my objective function as a linear combination of the gradient of the constraints. And this is a nice condition because this is linear algebra. If somebody gives you a point, x star, and tells you this is my minimizer, then what you do is you construct the gradient, you construct the constraint normals and form this matrix A star, and all you have to do now is find this lambda. So this is a linear system of equations in lambda. So a very simple way for checking. So solving a nonlinear optimization problem is hard. Checking that this is optimal is now easy. It's just a linear system of equations. And in fact, yeah. A is the Jacobian, yes. I should have written this down somewhere. So A star is the collection of gradients and throughout I'm using the convention, I think I had it on the first slide, that grad f star is the gradient of f evaluated at a point x star. So this is my abbreviation that I'm using. So this is the Jacobian matrix, or the transpose of the Jacobian. There is a difference of opinion between the United States and Great Britain as to which way around you organize your Jacobian, but we're not going to worry about that here. So what this is saying is I can write the gradient of my objective, and I have an old picture here that's not very good, unfortunately, as a linear combination of the constraint gradients. And this linear independence constraint qualification then implies that the rank of this matrix, it has to be full rank, and so the rank is M, and then I can actually form what's known as the generalized inverse. So that's this matrix here, and I can solve the system of equations by multiplying my gradient by the generalized inverse. So lambda star is also a solution to this problem here. I'll just move on from this. Okay, so now for inequality constraints, it's harder, but it's not, because we're going to do a simple trick here. We're going to say, for inequality constraints, I will have some of the constraints which are active, so they hold with equality, and then some of them will be inactive. So I'm going to use the same picture here, and I'm now going to make it into an inequality constraint problem. And what I do is I shape the area that is infeasible. So now this constraint is g1 of x less than or equal to 0. And the feasible set, this is feasible here. And there could be a second constraint, but we're not going to be concerned about it. If we're at this point here, somewhere around here, there could be another constraint that says g2 of x is less than or equal to 0. But at this point here, one of them holds this equality, that's the first one, and the second one is inactive. So locally, we don't need to worry about this constraint because the directions that we're interested in are only going to be concerned with the constraints that are active. So we can actually now reduce everything to the equality constraint case. So that's why we did the equality constraint case first. So again, we look at feasible directions. We apply the same mechanism that we applied earlier. So now we have an inequality constraint problem. We do a Taylor expansion of the active inequality constraints. And when we do that, we see that our condition for feasibility now is that the step has to be less than or equal to 0. So the condition is different to what we had earlier. Earlier we had inequality here, now we have inequality. So the feasible directions that we derive now are the directions that go into the interior. And so that makes sense on this picture here, the directions that we had for the equations were these two directions here, but now I can also take these directions. These directions are all feasible as well. And the directions that I drew here, they go strictly into the interior. So those are the directions for which S transposed, the gradient of G1 is strictly less than 0. You go strictly into the interior. So they're strict in feasibility directions, actually. And I know a few lectures ago, somebody asked about the Mahajan and Fromowitz constraint qualification, and this is what pops up in that constraint qualification. So exactly that condition. Okay, so we need, again, a regularity assumption, and so we can use the same regularity assumption that we used earlier, namely that the constraint normals of active constraints are linearly independent. And that's, I think, all you need to know. If you want to be fancy and pretend you know a lot about nonlinear optimization like I'm doing now, then you use big names like Mahajan and Fromowitz constraint qualification. But all this means is that you're looking at strictly interior directions, and it relaxes the linear independence constraint qualification. It's not as strong an assumption, and so it allows you to do stronger statements about optimality. But in most practical purposes, linear independence constraint qualification is all that we need, and we're not going to worry about anything else. Now, why do we need these regularity assumptions? And the reason is that there are examples where if they fail, then weird things happen. So here's an example where we're minimizing x1, so we're trying to drive x1 to minus infinity in this direction here. And we have two constraints. One is that x2 is non-negative, so we have to lie above the axis, to the top of this axis. And x2 is bounded from above by the cube of x1. So this is a sort of crude approximation of the cube there. My feasible set is this area here that actually extends all the way further to the right. And if you look at this point here, the origin, if this is your x star, then this is what's known as a cusp. And at this point, the constraint normals that you have are actually linearly dependent. So the constraint normal of the second constraint, x2 greater or equal to 0, points upwards. The other constraint normal points downwards. So this point violates linear independence constraint qualification. And in fact, there is this bogus feasible directions because the two directions collapse and point in the same direction that you would get out of those two constraint normals. There's this bogus direction towards minus infinity that pretends there is a feasible direction. And so because we don't have our constraint qualification is violated here, we have this bogus direction that's not really feasible. And if you try this example, and you can do this afternoon or over lunch, if you try this in AMPO, you will notice that the solvers will converge towards the origin. You start at a point 1, 1 or something, or 1.5, something simple. You will notice the solvers will converge towards 0, but then they get stuck and they want to make small steps towards negative x1. And each time they do that, they get told that that's not feasible, you can't do that, and they come back. And so there's this tendency to have very slow convergence. So this is a problem for which I think most solvers will exhibit very poor behavior, the nonlinear solvers. But it's because it's a problem that violates this constraint qualification. Okay. And so here's the main lemma that we have the first order conditions for optimality for inequality constraints. So the condition is again that the set of strict descent directions that are feasible is empty. And again, we can reformulate that and say there exist Lagrange multipliers such that this condition holds, where we can again write the gradient of the objective as a linear combination of the gradient of the constraint. So again, we're in the case where we solve a linear system of equations. Somebody gives us a point and tells us, I know this is the optimum. All we need to do is solve this system of equations. That's easy, okay? So there's one caveat here. There's now a sign restriction on the Lagrange multipliers. that has to do with the fact that we only go, we have these open directions, but we don't have the opposite ones. Okay, and so all this generalizes. You can put all this together. You can do equality and inequality constraints, and that gives rise to the Karish-Kuhn-Tucker conditions. So these are the Karish-Kuhn-Tucker conditions for nonlinear constraint optimization problems, such as the one that I have up there. So notice that I have a sign change now in my inequality constraints. It's greater or equal to 0, and that turns out, pops up over here for the Lagrange multipliers. So the condition is that if I look at the gradient of the Lagrangian, and I have not defined the Lagrangian, that's terrible. So the Lagrangian is actually the function that does this transformation that gives us the, so the Lagrangian at x and lambda is the function, is a linear combination of the objective function f of x minus the sum I from 1. I need to write it in this notation now, so that's I in E lambda I gi of x minus, actually I do this in a different way, sorry, union I. So it's the linear combination of the objective and the constraint functions. If you look at this for a moment, that's the condition that we had for the gradient condition, right? We had the gradient of the objective. If I take the gradient of this, then I get the gradient of the objective and the linear combination of the gradient of the constraints. And so that's my first condition here, the first order condition. And then what else do I need? I need to be feasible. A point can't be optimal if it's not feasible. I have this condition on the Lagrange multipliers that for the inequality constraints, they have the right sign. And there's this complementary slackness condition that says either I don't want the multipliers to be positive if I have inactive constraints. So if I have a constraint GI that's strictly positive for inequalities, then I make the multiplier equal to 0. For equality constraints, that doesn't concern us. Equality constraints will always be equal to 0, but inequality constraints can be both, in this case, positive or 0. So for zero inequality constraints, those are equality constraints. For those we want the Lagrange multipliers. For non-zeros, we don't. So in this picture here, the Lagrange multiplier of the second constraint at this point here, G2 of x star is strictly positive. And if I apply this complementary slackness condition, then that implies there is no multiplier. So lambda 2 must be 0. And that just means that this constraint doesn't participate in our expansion of the objective, of the gradient of the objective function in terms of gradients of the constraints. Okay, so there's a nice connection between this and optimization algorithms. An alternative way, and a much simpler way for explaining this, would have been to say, look, we have this problem up there. I don't know how to solve it. Here's a simple way of solving it. Why don't we do a first order Taylor expansion of all the nonlinear functions that we have and write down this linear optimization problem. This is a linear optimization problem in this step or displacement D, right? So first order approximation of the objective, and then first order Taylor approximation of all my constraints. If you write down the first order KKT conditions of this problem, you will get the first order KKT conditions that were on the previous page. So this is possibly a simpler way of deriving this, is to say, if we wanted an algorithm to solving this, then a first attempt might be to linearize everything and take a step and then repeat. That's a sequential linear optimization algorithm. And so this connection is interesting because we're going to exploit that in our auto approximation work later on. Okay, yeah. No, the KKT conditions of this are exactly these conditions. So if you look at it, If you have if D, oh, so the KKT conditions of D equals 0. So X star is a stationary point if and only if D equals 0 solves this problem. So that's the theorem. And if you get the dual of this LP, then you get the Lagrange multipliers, the lambdas that we had. That's right, yeah. So the dual of this LP, if you do the duality, then you introduce the lambdas that we had over here. So that's the connection. That's a good connection to duality, yeah. We must remember to say that next time. So that's, so X star is a stationary point if and only if D equals 0 solves this problem. And there's one difference here, sorry, I'll answer your question in a moment, but what's the difference between this theorem that I just said and the previous one? So my theorem is, I don't know where I can write this. So X star, stationary, then it follows D equals 0 solves this linear optimization problem around X star that I have there. So what's the difference between this statement? There's a lot of differences, but the key difference between this statement and the KKT conditions. Let's go back to the KKT conditions. What's the difference? So this says, anybody? Local minimum, okay, yeah, no, it's just bad wording there. It's stationary point versus local minimum. I could have done local minimum here. The difference is the constraint qualifications. I don't need constraint qualifications. So if, in this case, I think, I don't know, okay, so, yeah.
Is not a stationary point, then the minimizer would be the minimum value. What would be the minimum of D? Would be some positive value?
So if X star is not a local minimizer, then this will create a descent direction. D would be, and F star plus D transpose F of X star will be less than F of X star, and we can make progress in that direction. Yeah. Okay, so we derived nonlinear optimality conditions, and they require regularity, but we're only going to do linear independence constraint qualification. So with that, apologies for being slightly longer. We'll have a 5-minute break, and the next lecture will not be digital, but analog. So we'll go back to the old style of lectures. Cool, thank you.